welcome to this lecture on computer-aided power system analysis. So, we are now discussing the process of calculating line outage sensitivity factor. In that process, we have in the last lecture looked into the concept of Thevenin equivalent impedance between two buses as well as between a given bus and the ground. So, you would be utilizing those concepts for calculating the line outage sensitivity factor. So, just to recapitulate, so what we have said that Z, we said that Z even M n, we said that Z M m plus Z n n minus 2 Z M n. So, this we have already seen. Now, consider power grid. So, let us consider a power grid, any power grid. So, these blue lines are all buses, and let us say this, and let us say that this red lines are all lines. So, these red lines are all lines. There can be any kind of connection. So, I am just taking these connections, made it a highly meshed circuit. So, does not matter. So, let us say this is bus 1, this is bus 1, 2, 3, 4, 5. Now, when we are talking about LOSF, what we are just simply trying to find out that what would be the change in the power flow over the other remaining lines when any particular line is switched off. For example, if let us say the line between bus 3 and 5 is switched off, so then we would like to estimate that what would be the new power flow over this other line, that is this line, this and this. So, this is the basic purpose. Now, the point is that how do we really simulate the fact that this particular line is switched off into our calculation. Now, to do this, suppose this line has got an impedance, ZB. ZB is the branch impedance. So, ZB, let us say, is the branch impedance, of the line 3 5, say. Now, if I wish to simulate the outage of this particular line, what we can do is we can simply add another line between same two buses in parallel with the original line having an impedance minus ZB. So, what we are doing, what we are simply trying to do is we are adding another line in parallel with the existing line having an impedance of minus ZB. So, then therefore, their equivalent impedance of these two parallel lines with ZB and minus ZB. So, then Z equivalent would be ZB into minus ZB into ZB minus ZB, that is infinity. So, when it is infinity, it is as if that this particular original line is switched off. So, then if it is infinity, so then therefore, actually it is as if that this line is switched off, that this line is switched off. So, then therefore, we can simply simulate the removal of a line by adding a parallel line between same two buses having an impedance equal to the negative of the original line impedance. Now, how to incorporate this in our calculation? So, for this we have to again redraw our Thevenin equivalent circuit. So, if we redraw our Thevenin equivalent circuit between bus M and N, so let us say this is bus M, bus N. Now, here in this case let us say this is bus M, here in this case this is bus m. So, here m is equal to 5 and n is equal to 3. So, now what we are trying to do is, so we have got this, this, then this, then this, then this, then this, and this is z m m minus z m n. This is z n n minus z n m. This is v m 0. This is v n 0. And here this is z m n, which is nothing but equal to z n m. So, this is the Thevenin equivalent circuit, and this is bus m, this is bus n. So, please note that this Thevenin equivalent circuit is the equivalent circuit of the original network, in which this original line between bus m and n are is already existing. Now, I want to add another line in parallel between bus 5 and 3. So, then therefore, because in this Thevenin equivalent circuit already the existence of the original line been taken care of. So, then therefore, if I wish to add another line between bus 5 and 3 or bus m and n in the original circuit, that can be simply simulated by adding that same line between bus m and n in the Thevenin equivalent circuit, and this impedance is ZB, right. So, then therefore, when this line is connected, so then therefore, there will be some current which is going from this to this, right. So, let us say this current is I A, let us say this current is I A. So, then what would be I A? Now, if I add, so now I have to solve this current I A in this loop. So, then this current I A in this loop would be V m 0 minus V n 0 by Z m m minus Z m n. Let me write it in more elegantly. So, it is Z total, and what is Z total? Z total is, it is nothing but a series circuit. Z total is Z m m minus Z m n plus Z n n minus Z n m plus of minus Z b. Now, this plus this is equal to Z t h. So, then that is Z t h m n minus Z b. So, then therefore, I A would be equal to V m naught minus V n naught by Z t h m n minus Z b. So, this is the current I A. So, now because of this current I A, so then now basically there is now change in the injection current at bus M because of this addition of this current, because of this addition of this link having impedance minus ZB. So, then therefore, because of this addition of this link minus ZB between bus M and N, now there is a change in injected current at bus M and N. So, the change in injected current and bus M and N, we write it specifically. So, change in injected current due to addition of minus ZB impedance is delta IM is equal to minus IA and delta IN is equal to plus IA. It is obvious from this because change in injected current, now IA is going away from bus M and IA is coming into bus N. So, then therefore, change in injected current at bus M would be minus IA and change in injected current at bus N would be plus IA, right. So, then therefore, what would be the change? So now consider any two bus, P and Q. So, then now because of this change in injected current at bus M and bus N, so delta Vp would be nothing but Zpm into delta Im plus Zpn into delta In. So, if I put it, it would be equal to Zpn minus Zpm into Ia. Similarly, delta Vq would be equal to Zqm into delta Im plus Zqn into delta In, and if I substitute delta Im and delta In from here, what I get is I get Zqn minus Zqm into Ia. So, this is what I get, right. Now, the current, now now the current, so then delta IPQ, now what is delta IPQ? So, the change in current flow over the line PQ would be what? That is given by delta IPQ. IPQ is the current flow over the line between bus P and Q. So, it is delta IPQ. So, then that would be is equal to delta Vp minus delta Vq by Zc. What is Zc? Zc is the impedance of the line between bus P and Q, right. So, this is the impedance between bus of the line between bus and Q, and we again note here that ZB is the line we must also we must also note that ZB is the branch impedance of the line. So, then here we should also write that ZB is impedance of the line between bus M and N. Please note that this impedance of the line between bus M and N, and we are simply trying to analyze the effect of this outage of this line having impedance ZB on the remaining lines. So, that is what we are trying to do. So, then therefore, delta I P Q would be delta I P Q is delta V P minus delta V Q by Z C. So, now I substitute delta V P and delta V Q. So, what is delta V P is Z P N minus Z P M. So, it is Z P N minus Z P M minus delta V Q is Z Q N minus Z Q M. So, it is Z Q N minus Z Q M divided by Z C into I A. We have done simply substituting delta V P and delta V Q from the original equations, and we get this. So, then therefore, we can write down that delta I P Q is simply Z P N. So, it is Z P N minus Z P M minus Z Q N minus Z Q M. We should take some ZC. We should actually write this is ZC. So, when you are writing with small z, that denotes the line impedance, and when you are writing with capital Z, that denotes the element of the bus impedance matrix. So, these two are very important, because often we make mistake that we do simply confuse between these two. We need to note that this ZC, this ZC and this ZC, these are nothing but the individual bus impedance. So, then therefore, what I should also do it here is as follows: ZC, and here also similarly here also we also should write ZB should be a small one. Actually, that should be a small one. Should be a small one. Take a small z, actually this is a small z. So, this is a small z, small, these are all small z, also small z, this is also small z. So, we have just spent some time on this, and this is IA, and IA we have got the expression of IA is Vm this. So, we Vm minus V naught. So, this is Vm naught minus Vn naught by Z theta H M n minus small z b, small z b. So, this is the expression. Now, what we do have? So, then that I can write down as Z P n minus Z P m minus Z Q n minus Z Q m by Z Thevenin m n minus Z b. We are purposefully writing it as small, and we are doing something that Vm minus Vn0 into Zb into Zb by Zc. So, what we have done, we have simply taken it here. So, this divided by this and this divided by this, we have simply done this divided by Zb into Zb by Zc. Now, what is Vm naught minus Vn naught by Zb? Vm naught minus Vm naught by Zb is nothing but the original current flow through bus Mn. So, we note that Vm minus Vn naught Zb is Imn naught, right. So, then therefore, what we can write down is delta Ipq is equal to Zb minus Zc into Zpn minus Zpm minus Zqn minus Zqm by Z theta Hmn minus small zb into Imn 0, right. So, then therefore, change in the line current over the line PQ with respect to the original current flow over the line Mn, and the line Mn is the line which is going, which is actually experiencing outage. So, then therefore, delta I PQ by Imn 0 would be given as, so then therefore, delta I PQ by Imn naught would be given as Zb by Zc into Zpn minus Zpm minus Zqn minus Zqm by Z theta Hmn minus Zb. So, then by this, if any line is getting outaged, so then we can simply estimate that what would be the change in the current flow over any line by this simple expression, and in this simple expression everything is constant, because now here we need to note something very carefully so that we do not do any mistake. There are some quantities which are the elements of the bus impedance matrix. So, elements of the bus impedance matrix are this, this, this and this. So, these quantities are elements of bus impedance matrix. This is very important. So, this is elements of bus impedance matrix, this is also 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 elements of bus impedance matrix. On the other hand, these three quantities, this, and this, so these quantities are the impedance of the individual line. So, while calculating this, we must be very careful about this, that which element denotes the individual line and which element denotes the elements of the bus impedance matrix. So, until and unless we are careful enough, we would be making a lot of mistake. So, this must be very carefully understood and appreciated. Now, here we have got the change in the line current over any existing line because of the outage of the any given line. But when we have started discussing the concept of sensitivity factors, we said that we are actually trying to estimate what would be the change in the power flow, that is basically the real power flow over any remaining line due to the outage of any given line. So, then we need to now connect this expression with the expression of the power. So, to do that, we have to again take recourse to our basic assumptions of. So, we now need to again recollect assumptions of the DC load flow. So, assumptions of DC load flow, we have to recollect assumptions of DC load flow. So, what are these assumptions of DC load flow? We very quickly recollect them. One is that all Vi is equal to 1.0. Second is that theta I, all theta I is almost equal to 0, but not equal to 0, of course. So, then therefore, theta I minus theta j is also almost equal to 0, and then all resistances are neglected. Of the lines are neglected. So, these are the assumptions of the DC load flow. So, utilizing these assumptions of the DC load flow, in the next lecture we will see that how this same expression can be used to calculate the change in real power flow over an existing line because of the outage of any given line. Thank you.